Welcome everybody to another week of NLP with Friends. We're really excited to have Data and Adelani here for this week's talk. Just a couple reminders. We're going to have a Q&A session at the end, and if you want to ask questions then, we'll collect them on Dory. The link is in the chat and also the email where you got your Zoom link. If there's any pressing questions you want to ask that will help with your understanding going forward, feel free to use the raise hand function in Zoom, and we'll try to make sure that those get resolved. So yeah, I'm gonna turn it over to David, who is a PhD student at Saarland in Germany. And in addition to the work he's going to talk about today, also works on privacy in dialogue and other spoken systems. So now I'm going to turn it over to him.
Okay. Hi, everyone. Thank you, Elizabeth, for inviting me and the other organizers. So this afternoon, I'll be talking about, or maybe it's in the morning in other places, development of NLP data sets and models for African languages. So my motivation is to encourage evaluation of NLP models across diverse languages. And the reason is just because majority of the world languages, most of the world languages are in Asia and Africa. And interestingly, when you think about the number of speakers for all these languages, aside from Europe, European languages are spoken worldwide. We also have an average number of speakers for African languages is pretty high, like 30,000 per language. So apart from that, we also need to increase geographical diversity of NLP researchers because there are other issues in NLP like bias to certain groups, and we need this diversity also. Is one of the ways of addressing this problem. Yeah, so this is the outline of my talk. First, I will talk about the challenges of text quality, issues in online resources we have for African languages. Then I will talk about comparing massive and curated word embeddings for African languages with focus on Twi and Yoruba. And then I will discuss our recent work on transfer learning and distance supervision for name-based recognition with focus on 3 African languages, Hausa, Isishosa, and Yoruba. And lastly, I will end my talk with developing our data sets and models for over 10 African languages. Yeah, the first part is the problem of text quality in online sources. So the most popular resources for African NLP, I would say probably is the Bible, because this is available in almost in a lot of languages. We have a lot of translation, over 1,000 in African languages. This is quite impressive. But this is biased to the religious domain, so it doesn't generalize to other domains. And another good source that we have recently is the JW300. This covers over 100 African languages, and the quality is pretty good. Of course, for some of the languages, there's still some challenges of quality. And we have the noisy corpora, which is Wikipedia. For high resource languages, Wikipedia is a very reliable and a very high quality source. But for low resource languages, we have very few articles. Like African language, we have around 38 African Wikipedia pages. And when you look at the number of articles that is being covered, it's less than 500,000 articles. And most of the time, the articles are very short compared to the longer text that we have in English. And just English has over 6 million articles. So that just to tell you that we do not have a lot of text on Wikipedia. And this affects the kind of models you build using Wikipedia. Another one is the Common Crawl, which is very noisy. First, they have to do automatic identification of the languages, and which is not perfect, and there are issues with that because closely related languages are being assigned the same, uh, are being assigned the same language type. And we also have some news media like Voice of America, BBC, actually that have African languages. So I would say probably the 10 most resourced African languages are probably Afrikaans, Swahili, Malagasy, Somali, Amharic, Hausa, Yoruba, Kinyarwanda, Zulu, and Tingrian. But Yoruba and Kinyarwanda actually have a lot of quality issues because Kinyarwanda is probably mixed with Kirundi and a sister language very close to it. And this is part of the problem with the automatic identification of languages in Common Core, for example. So some of the known text quality issues are like some languages are often spoken, but they're not written. So for example, Bambara is a very big language. It's spoken in about like 8 or 9 West African languages. And of course, the Bible is available, but it's not, we don't have a lot of written text. So most of the speakers actually speak French and they are taught French in school, but they are not taught to actually write their language. And this is a big challenge for NLP research. And this Bambara is what is used for trade. So, but we don't really have enough data for NLP. So we also have like code switching corpus. For example, in Senegal, Wolof is probably mixed with French, and in Gambia is mixed with English. And most people cannot say a complete sentence in Wolof without adding either French or English. This is also a problem. And we have like mixed dialect problem where in the same text, you have like multiple dialects are used. For example, in Twi and in the JW corpus, they mix the dialects. We have the Kinyarwanda Kirundi, and this is mixed together. And we have also Fula with different writing styles and also different dialects. The last one is diacritics problem. This is very common for Yoruba and other languages that tonal, like Fon, that is spoken in Benin. So this is an example of the mixed dialect problem in Twi. This is the Asante and the Akupem dialect, and they only define one character. It's not really a lot of difference, uh, but this is very common in JW300 where they use different dialects. And another one is Kinyarwanda and Kirundi. And you can see that the texts are very different. They actually mean almost the same thing, but they look very different. But in Voice of America and BBC, oftentimes you cannot distinguish between Kinyarwanda text and Kirundi. So this is a big challenge if you want to really, for example, if you want to train embedding for Kirundi. Another one is Fula dialect. Fula language is a very interesting language because it's spoken across West Africa, also to Central Africa. And just because the speakers of this language are nomads, so they move around a lot. So, and over history, also the language has changed a lot. So, and it's written uh, with different alphabets and influenced by different culture. So because of that, we have so many dialects, and some are actually have a lot of resources like the Pula, Nigerian Fufude, Adamawa Fufude. So they have quite a number of resources online. So the Yoruba diacritics problem is without the diacritics like tonal marks on top of words or the under dots, the pronunciation only depends on the word context. So like word like owo, so I've been normalized in most written text online as OWO. And actually we don't, there's nothing like OWO in Yoruba. There's no word that is called that. But oftentimes on smartphones or social media, people just write this without diacritic. Initially, the problem was because there was no keyboard like on mobile phone and all that. But the problem has been solved. We now have Google Gboard like on the smartphone, and we have Yoruba keyboard. But people are still resistant to write with the correct diacritics, and some don't even know it. And this is a very interesting example I saw on Twitter where someone said, "What is alejo in English?" Apparently, alejo means a lot of things. So over 10, I would say, meaning for alejo. So this is the main issue with NLP for some African languages. We can address this problem by, for example, doing automatic diacritic restoration for Yoruba. For example, we can use sequence-to-sequence model to predict what would be the right diacritics of a word based on its context. So, for example, we can have a source sentence without diacritics, and we ask the sequence-to-sequence model to produce a sentence with diacritics. This is just like a machine translation uh, kind of a problem where we translate from an undiacritized text to a text with diacritics. So other practical solution is that, I mean, it would be very nice that we educate native speakers to write articles in their language. For example, in Bambara and other languages, it's good to standardize the writing system. This has been done for a few languages like Hausa, Yoruba. It would be nice to also have this standardization for Twi. Maybe for Fula will be more difficult because people are scattered around. And it's very important to involve native speakers in data set collection to identify the quality issues. Another thing that is important is that people should write a data sheet for their data set so that we know what are the quality issues. And this has been popularized by Emily Bender. Uh, Another one is that there's need to have more language identification models, not only to identify languages, but to identify dialects of language. And also standardization of low quality text, either through by humans or by machine learning models. For example, adding diacritics to Yoruba text automatically. So that's the first part of the talk. The second part, I'll be discussing our work on word embeddings for Yoruba and Twi. So word embeddings, like probably most of you know, is just a vector representation of a word. So and this vector representation captures syntactic and semantic relationship. Syntactic relationship, for example, like king and kings, actually the word representation should be close to each other. And also semantic relationship, man and woman should be close to each other. And we could even do interesting arithmetic operation like the vector of man plus vector of woman minus vector of king should be similar to vector of equal. But the interesting thing is that this one embeddings are trained on a lab text, which is not available for most African languages. Like the English, like Glove was trained on 6 billion English Wikipedia words. I mean, we don't have that. And we have fast text embedding. This is very nice because it was trained on multilingual Wikipedia. So I think they trained on over 294 languages, Wikipedia, but some of the languages are very small. They only have very small number of articles. But the question is, what is the quality on low resource languages? After listening to the first side of the talk, you know there are a lot of quality issues, and you're not sure if the word embeddings actually are very good. What Facebook trained? Uh, can we really use them? That's the question. So we evaluate this on two languages, Twi, that is native to Ghana and West Africa, and Yoruba native to Nigeria. Twi is tonal, but the tones are not represented in the text. So, but the problem is that they only have few articles online, and most of the articles also they use mixed dialects. So that's one issue. And Yoruba is tonal, and the tones are represented in the text. So you have this diacritics problem. And most texts you find online actually ignores these diacritics. So we evaluated on these two languages. Um, and when you think about what are the limitations of the pre-trained word embeddings, the first problem is that there's a small training data available on Wikipedia and Common Core. So for example, the TWI Wikipedia currently has like just 20,000 tokens. I mean, you cannot have, expect a good quality compared to like 6 billion tokens trained on English Wikipedia. And all these neural network models are actually data intensive. So Yoruba Wikipedia is larger, as like 500K tokens. Another problem is the low quality training data. Oftentimes very noisy, we call them noisy text. So Yoruba has that, the critics problem, Twi has like this mixed dialect problem. And another thing is that when all these models are trained, there was no evaluation on low resource of languages. They evaluated on English mostly, And for example, FASTA is probably evaluated on some of the European languages, but still there is no evaluation in African languages, for example. So we created like an evaluation data set. For us to do this, first we translated WordSim 353 from English. It's a standard benchmark for evaluating word similarity in English language. And this also has human similarity scores. So what people have done in other languages is that they translate what's in from English maybe to Czech or to Dutch or Spanish, and they compare what is the Spearman correlation between the human evaluation and the embedding similarity score, maybe in another language. So we are doing exactly the same thing here. So, and for us to compare, we also curated some data set. First, we we have a small data set for Yoruba, like 1.6 million tokens. And you can see it's a lot of just gathered like small pieces of text that we think are clean. And first we have all the clean text up to this place. And after that, we have C2, which is just all the clean text in C1 plus BBC Yoruba. BBC Yoruba is still an ongoing fight that they should improve the quality of their news articles because they do not use the standard Yoruba text. And for TWI, the C1 was just the Bible. Actually, for TWI language, the cleanest was the Bible. And we added Wikipedia text to it, which is also a noisy text. And we see what would be the Spearman correlation for C1, for C2, and C3 is just all the available data set we could find. We just combine everything together and see what happens. Maybe more text just is, if you have a lot of text, maybe that just solves the problem. So why bother yourself about this multiple dialects problem or that business problem? So we train word embeddings with some word units. For example, we train fast text, and fast text, what they do is that they have the word representation for a word, which is WJ, and you sum it with all the word representation of character engrams, and you can average over all the available embeddings you have. And for the CWE, this kind of include character embedding. So you have a word embedding, and you also have character embedding. And actually, there are different variants of CWE because you can actually check if this character is in the beginning or in the middle or at the end of it. And this way, you can also do some clustering so that you can have like a more representative character embedding. So you average them together, and this is how you have the CWE. So we check uh, what is the performance of this word embeddings using these two models. Because, for example, the TWI is more influenced by different like characters. So our evaluation on fast text is the following. First, we evaluated the WordSim 353 on the pre-trained embeddings. The first one is trained on Wikitext, and the second one is trained on Common Core plus Wikipedia. And what you can see is that they have very low speaker correlation. First, for the tweet, it has a very small number of text, and that's why we have this very low speaker correlation. And the vocabulary is very small. And for Yoruba, it has a larger vocabulary size, but the speaker correlation is also still small, just because of the quality of the text. Then we find Common Core. Common Core has more data, but you can see that it actually has lower Spearman correlation. This is just because of the quality, because upon inspection of the vocabulary, we find a lot of words that are just English word, French, and Arabic. And this was used to train, so this completely degrades the performance. And when you look at a very small data set that we have, we are able to have very good, I mean, kind of okay, like Spearman correlation over 0.3. And that means from 0.3, we know that embedding can be useful, at least for other tasks. And for C2, we found out that for TWI, adding more text, like adding Wikipedia, kind of, it's like diversifying the text and actually gives better performance than just the Bible. And for Yoruba, we actually find that it degrades the performance because we just added BBC. And BBC is very noisy and actually degrades the performance. And we use it where we just combine everything. For Yoruba, the JW300 was added and it's over 10 million words, but it's actually the JW has very good quality diacritics. So this improves the performance. And we did the same evaluation on CW, and we have the same trend. The only thing is that we have this surprising, very good result for TWI, because maybe just because of the Wikipedia text we had, it's able to understand more concepts. But we find out that for Yoruba, the result is pretty similar. And another probably interesting thing is that if we compare the result for fast text and Yoruba, we see that probably CW model is better for TWI and FastText is better for Yoruba. So then we move to contextualized embedding. Is the observation also true for contextualized embedding? Static word embeddings, of course, have their own limitation. For example, you cannot use this for word sense disambiguation because like a word like bank can mean different things in different contexts. It could be a river bank or a financial institution. So the embedding of a bank should depend on the context. So we experiment with one of the most popular contextualized embedding, which is BET. And for the evaluation, we use name entity recognition, which is a task to recognize like entities like personal names, location, organization, or date. And the evaluation data set is the global voices Yoruba text, which we annotated in the course of the project. And although it's a very small data set, like 26,000 tokens, but at least it's able to, we can use it to evaluate the quality of the embeddings. And this is the data statistics. Yeah. So when you look at the evaluation on BET, the first thing we did was we lowercase the NR data. And because capitalization is an important feature for any models. And also Stephen May also confirmed this in his paper last year. And one thing we can see that if we use the pre-trained on case multilingual BET, we have an F1 score of just 27%. And if we fine tune, because we could not train BET from the scratch for two reasons. Number one, we don't have enough data. Number two, probably we don't have the resources. And you can see that by just fine-tuning, multilingual BET on Yoruba text, and now fine-tuning it on an NAR task, we can double the performance. And just this is just telling you about the number of Yoruba text they have in the training data because they use Wikipedia. And Yoruba text on Wikipedia are quite small. Another thing is that we did another thing where we just replace some of the vocabulary words of the multilingual embedding, and we just replace it by Yoruba words. And we find out that, and we fine-tune the max language model again before fine-tuning on the task. And we find out that this even further improves the performance by like 4%. So, I mean, we have there are challenges and future work for word embeddings in low resource languages. I think one of the interesting things would be how do we portray the contextualized embedding for low resource languages? Would you leverage on maybe parallel data or use some cool ideas from machine translation to do this? And also there is an ongoing problem like, okay, how do we expand the quality data set that we have in low resource languages? So yeah, I will now move to the third part of my talk, which we started with this African NLP workshop earlier this year and with a lot of collaborators here. So this is based on transfer learning and distance supervision for name entity recognition. NER is So it's a core NLP task which involves recognizing entities like personal names, location, organization, or date. It's a classification task, and an example you can find here on the 4th of February. 4th of February is the date. Global Voice is an organization. Fernando Gomez is a person. But for high resource languages, they can reach an F1 score of 90%. But this is much lower for African languages. Like in the BET, the highest we could reach was like 60% of that. Yeah. So, and for low resource languages, there are many opportunities. For example, we could see what is the impact of different pre-trained word embeddings. We could do distance supervision by uh, like allowing experts to write rules to automatically annotate some of these entities. And also because this results into errors, so we can handle the label noise errors. And we can also do transfer learning that is very popular now. So now we kind of extended to three African languages. Now we are so we study like Hausa and Yoruba spoken. Hausa is spoken is native to Niger Republic and Nigeria. Is spoken actually in West Africa and Central Africa. And Yoruba is native to the Benin Republic and Nigeria. And Isishosa uh, is native to South Africa and is the second most spoken indigenous language in South Africa after Zulu. So then we evaluate all our methods on NER data set. We have an NER data set for Yoruba based on our previous work, and it shows that they already have NER data set for all the South African languages since 2014. And for Hausa, we just created a fresh one using the voice of American news articles. So, and for our work, we use like word embeddings like Word2Vec and fast text. We use Word2Vec for Hausa and fast text for Yoruba. And we use by LSTM and LSTM character CNN plus CRF. Yeah, we also tried contextualizing embeddings like multilingual beds and XLM better. And one interesting thing you can see is that, okay, if you use fast text and LSTM model, they have very small number of parameters. But the question is that does it worth it in low resource settings to actually go for these large models with over 100 times more parameters? So first we talk about training data through distance supervision. So annotation is always expensive. So, and especially for low resource languages, maybe you don't even have access to the native speaker of this language. But peradventure, you're able to get like a very small few sentences, like 10 or 100. Can you use this, can you leverage on this to have some automatic annotation? This is the kind of problems we're talking about. So also even in the low resource setting, we still have access to a large unlabeled data compared to labeled data. So we can do some automatic annotation for this. And this is quick and cheap. And we could leverage on the context, expert insight, maybe even external knowledge or resources like Wikipedia, where we can extract like all the locations, for example, all the organizations, names from Wikipedia, and we can try to address the noise aspect of the labels later. So for distance to supervision, you always probably sometimes you need a native speaker who is the domain expert. So for example, this is quite interesting when we started working on this. If you want to detect dates in Yoruba, apparently we found out that for every date that's written in Yoruba, they always use date keyword. So you have like Ojo is for day and Oshu is for month. And every date always have this. So we can use this date keyword and just look at the side and say, okay, the next word after this date keyword should be a date with high probability. So we can use this to automatically label that. And we find the same thing in Hausa that they also have this keyword like Rana, water, for the day and month. And we can use this to automatically label. Yeah. So, but apart from the date, we can also use entry lists like from Wikipedia or Gazette or phone books to label like personal names and location. But unfortunately, it's not every time that we can find the entries. Maybe we are not able to find global voices because Wikipedia did not list it and it's not in other uh, yeah, entry books. So what can we do to address this? Uh, I mean, when we do automatically annotation, of course, some of the labels are noisy because they are not accurate. So, can we do anything at the modern aspect to handle this noise? So, this is an example of the distance supervision we did, where we automatically label both from domain expert and from automatic annotation from Wikipedia. And we find out that for Yoruba text, we're only able to annotate just few things for personal names. Location is better, maybe just because some popular locations do not change any form in Yoruba. And dates is also kind of okay, but we have some noise and we want to uh, address this problem of noise while training the model. So we use some noise modeling techniques where we have a base model, for example, a by LSTM, and it has its own parameter. Then we can add a noise model to it that has it's also trainable parameter, and we can now combine all the clean examples and the and the noisy labels. We can combine them together. So there are many approaches for handling this noise. One example is that you can use the noise channel, where all the examples you have, whether clean or noisy, they go through the base model and the noisy model. And the noisy model is robust enough after training with EM algorithm so that it limits the effect of the noise level on the final annotation. And another approach is using the confusion matrix. Confusion matrix is this is what we do on a classification task. So we can compare all the clean labels and the noise label for the few examples we have. And with this, we can have a confusion matrix. And we can use this to initialize our noise model. But this noise matrix is still trainable, and over time it's going to change based on after training the model. And this makes the model to be more robust to the noise level and even improve the performance. Another approach is the noise cleaning approach. So in this approach, the distance supervision data is first sent through a cleaning model. So basically, this cleaning model tries to clean the labels a bit, and you have the base model that has some clean examples, and you try to combine the cleaned. So you now gently train on the cleaned labels and the clean examples you have, and you train this in a multi task fashion. So these are our results on Yoruba. As you can see, if you only train on the clean text, for example, if you have like 1,000 tokens, the performance is very low, it's less than 10. But if you just combine it with, you just automatically label a large chunk of text and you add it with it, we kind of more than double the performance of this. And we added some noise handling methods to it. And this gives us some slight improvement with this. So the question is that if you have this very good result, so you can improve just by combining clean and distance. But the question is that if you use a more complex model like BERT, do you still need like these additional examples? Uh, yeah. And so we train it on BERT, and we find out that just with 1K, you have like more than twice the performance you had with the fastest. And if you combine it with the distance supervision, we can also further improve. But the more training data you have, we find that at some point, these noisy labels, noisy example, they start affecting the performance and actually it doesn't improve again. So we need noise handling techniques also for BERT models. This has not been done before, so we work further on improving this. Yeah. So yeah, but the problem is that do we always need these complex models in low resource setting? Um, Maybe we can have like a simpler model that give like the same performance. So we evaluated on Hausa and Isishosa. Actually, the performance we have in Hausa is very similar to Yoruba, so I did not put the Yoruba on this figure. So if you use a very simple model, GRU, we have this trend that the more number of sentences you have, also, yeah, of course, the performance improves over time. And if you use a more complex model like the LSTM, CNN, CRF, uh, we even have a better performance. And with the SLM Roberta, we have a superior performance. But when we come to issue social, uh, I think recently, I think Lobster and POC, they published a paper and they say that just a simple CRF that is linguistically motivated. So you have these features, maybe using the post tag and other low-level features, they could reach a better performance than LSTM. And that's the point, that's the red point here. And even with the XL level better, we are not able to reach the performance just because of the some of the writing style of Isishosa. Even from the way I wrote Isishosa here, you sometimes they have like lowercase before capital letter, and some features are just completely missing. That's all these neural network models overfit on. And we find that a simple CRF model is better for this language. So we added also noise handling method for the BERT-based models. We used the confusion matrix to get better performance last time. And we have some small changes to this because if you have a very small data, it may not reflect the actual change in the noise distribution when you try to compute the confusion matrix. So we apply these smoothing techniques that is based on adding smoothing to matrix-based noise models. And the smoothing is as follows. All the entries of the confusion matrix, we, we raise to power the beta, and we now normalize uh, we normalize by the rule sum. And I think in the paper they suggested having a beta of 0.8, so we just use the same in an output. And this is the result of our analysis. For AUSA, what we find out that for very small number of sentences like 10, we find that using distance supervision actually helps because you can go from around 25% to more than to close to 60%. But the more examples you have, things are not very clear again. Distance supervision always at least helps to when you have like uh, I would say like 200 examples, but after that it doesn't help anyway. And it's not very clear whether confusion matrix helps or not, even with the smoothing techniques. But for Yoruba, we find out that uh, the noise matrix gave better performance than the distance supervision, even up to like 300 sentences. And when we use the smoothing technique, actually give the best result. Uh, and this is very good for in the low resource setting. So apart from this distance supervision, we also tried the transfer learning. And what we did is as follows. First, we fine-tune on English Colonel uh, data set before fine-tuning again on few examples of the African language data. So it's like two levels of fine-tuning. And for the Isi Xhosa and Yoruba, we can see that this actually helps. Even with just 10 examples, if you do zero shot, you have like just 10%. And if just adding just 10, 10 examples, we could reach a performance of more than 40% in few short seconds. And this is even better than just training the XLM. And we observe the same thing for Yoruba, which is quite impressive that just with 10 examples and with few shots, you can go from 50% to close to 70%. And actually, we find that even this improvement is one bigger than what we experience in the distance supervision. Yeah, so that's all with my talk, and I will wrap up with what we are doing to create more NLP data set for African languages. And this is with Masakani. Initially, they were working on machine translation, and now it's now Masakani NLP, and we have other tasks like NAR. So for African languages, we do not have like large NLP data set in the news domain. All we have created for Hausa is just like 50,000 tokens. For Yoruba, it's like 26,000 tokens. So these are very small. They're not like the standard benchmark data set. And this is what we're trying to do now. Currently, we are working on this like 12 languages, and we hope to increase more if we have more volunteers to annotate the text. So if you speak any of this language and you want to help with the annotation, please reach out. Yeah, I think that's it. Thank you. And thank you to also some of my co-authors and collaborators, my lab members and Masakani community. Thank you very much. That's it.